Hello, everyone. We are proposing to create a biocompatible septal occluder for tissue growth. My name is Rachel Arnold.
I'm Joelle Hanley.
I'm Miriam Sayegh.
And I'm Faith Stewart.
Every year in the United States, 2,118 babies are born with atrial septal defect. Last year, I found out the hard way that I was one of them. I had a cryptogenic stroke and found out that I had a patent foraminal, which is the most common type of ASD. I had a Gore cardioform septal occluder placed to close my PFO. Upon further investigation, existing septal occluders can have life-threatening consequences. We're here to tell you about a more cost-effective biocompatible solution.
Arterial septal defects, or ASD for short, are one of the most common forms of congenital heart disease. They occur when communications between atria fail to close at birth. Larger defects may require percutaneous or surgical closure to prevent complications in the future. And the current method used to treat a PFO is a septal occluder made of either EPTFE or polyester membrane and a nitinol wiring. It is known that nitinol degrades and releases nickel particles, potentially causing nickel toxicity or allergic reactions. The current device can also cause tissue erosion. Our clients are mainly biotech companies, and our customers will be doctors, surgeons, as well as patients suffering from ASDs. We believe that our device will prevent complications such as recurrent clots, strokes, pulmonary hypertension, dysrhythmia, as well as other problems associated with current designs such as allergic reactions and foreign body response.
Our occluder design will be a flat dumbbell-shaped scaffold with seated cell patches on the inside of each end, as well as cells seated over the connector. The occluder will be inserted through current methods with the use of a catheter and will be placed with an end on either side of the ASD, with the connector through the center. When placed correctly, the cell patches will touch the septal wall. The dimensions of the device are listed in the figure shown, and the ends will be twice the size of an average ASD since this is not a self-centering design, while the connector length is the average thickness of the septal wall. The cell patches will consist of cardiomyocytes, HGF, and IGF-1 to promote tissue and cell growth and increase viability and cardiac stem cell differentiation. The cardiomyocytes will be derived from induced pluripotent stem cells as they produce viable cells that are not allogeneic. There will be approximately 250 million cells needed for the entire device. These cells will be cultured, and then gene transfection will be performed to incorporate the DNA for HGF into half the cells and the DNA for IGF-1 into the other half, so that HGF and IGF-1 can be produced in vivo. After, the cardiomyocytes will then be seated onto the scaffold. The scaffold will be made from collagen type 1 and silk fibroin in a ratio of 7:3. Based on the dimensions of the device, as well as the material properties, this will require approximately 6 milligrams of collagen type 1 and 598 milligrams of silk fibroin to fabricate the entire device. The collagen and silk fibroin will be electrospun to create the scaffold.
Our device is beneficial in that it provides a biocompatible alternative to traditional occluders that use metal. This table provides a comprehensive summary of the limitations of current devices on the market as compared to our device. An X in the chart marks a limitation associated with a specific device. The green boxes show that the device would not elicit that limitation. As you can see, our device would not cause any of these limitations, and that is because we are not incorporating metals into the device. The use of metals can elicit unwanted tissue responses, such as those listed in the table. Many of the reactions occur because of tissue erosion when nitinol rubs against the atria and aortic root. This interaction can cause excessive bleeding and cause the heart to function ineffectively. When this occurs, the occluder needs to be removed, but the hole still needs to be closed. Most times, open heart surgery would be required, defeating the minimally invasive device design. Our device circumvents the need for revision by incorporating materials that are biocompatible.
Our projected cost for the materials we have proposed is approximately $3,500, which is sufficiently less expensive than the existing devices on the market, which have a base cost of around $8,000. Since the materials are purchased in bulk, they can be stored in cryofreezers to preserve them for many uses. Medical devices such as this are typically purchased by hospitals for doctors and surgeons to implement. The cost of associated implantation would be covered by patients and their insurance companies. To purchase the initial materials, medical grants could be a potential source of funding. As mentioned previously, current devices on the market can cost upwards of $8,000, and complications can cause the cost to raise over $50,000. The current devices also have a success rate of 95%, which means that the 5% of patients who use these devices do not have a successful experience. This could include death, open heart surgery, heart failure, etc. We believe our device will be able to surpass the abilities and advantages of current devices on the market and would be more beneficial for the patients. Thank you. Does anyone have any questions?